on this example, I wanted to introduce a force that is tampering with the normal force. It's really important to realize that the normal force is not always just mg. You have to really look at what's happening vertically to figure it out. So we'll start with number A. I have a 12 kilogram block. I'm pushing on it with 75 newtons of force. So let's see, I got that. And we have some kinetic friction, so I'm going to write that up in here. It's just easier than trying to look in the paragraph to get it. And I've got my 75 newtons applied to the block, so that's good. So I want the acceleration of the block, and I start putting in force vectors. Force of gravity matters because that helps to create the normal force. So I have 12 times 9.8. Oh, I think I just did that in the previous problem. 117.6. And I have a normal force pushing up. That is the surface pressing on the block to keep it from falling through the surface. So if that surface has any integrity at all, then it's going to cancel that force of gravity. All right, I don't have any other forces tampering with the vertical direction, so I can say that the normal force is just equal to mg. The block is sliding to the right, which means the kinetic friction force is going to oppose that direction of slipping. And just to keep my diagram clean, I'm not going to put any details about the kinetic friction yet. Okay, so I want the acceleration of the block. I've already done the vertical force analysis. I used it to find the normal force. Then in the horizontal force analysis, I'm going to apply Newton's second law. I'll be a little more formal for a second. And just remind you, we're looking only in the x direction. And so 75 newtons to the right, I'm going to call that positive, minus Fk is equal to max. All right, but Fk is going to be mu k times the normal force. Just plugging things in. Mu k is 0.35. My mass is 12 kilograms. And I can solve for A. And I get 2.82 meters per second squared. All right, let's see how the second problem is different. So I'm using the same magnitude for the force, but it's up at an angle of 50 degrees. So that has two different consequences. If I look at the components of this force, there's a little bit of it pointing to the right, and a little bit more of it pointing up. So my rightward force has been reduced. And then the second part is that I now have a vertical force pulling up on the block. So I'm just going to call that Fy for now because I don't have a lot of room over here. And then this is Fx. And this vertical component actually changes the amount of normal force. So just the qualitative stuff first. I have the force of gravity pulling down. I'm not even going to write the calculation again because I just did it, 117.6 newtons, and then I have some normal force, the floor pushing up on the object. So just qualitatively, I'm partly pulling up on this thing now, and it makes it so the floor doesn't have to push up as hard to keep the block up. So the normal force is going to be smaller than it was before. It really bothers me not to have these little hash marks, so I'm just going to do them real quick. I don't know why, it's a long tradition in physics that surfaces have hash marks. Okay, and then this block is sliding along with some kinetic friction force operating to the left to oppose the direction of the sliding. So now my vertical force analysis is less trivial. So I'm going to look at F net in the y direction. Well, there's no acceleration in that direction. Assuming this vertical component is less than 117.6 newtons, the block isn't going to pop off of the floor. And I look at my upward forces, that's N plus Fy. So Fy is going to be 75 sine 50 degrees. That's all the upward stuff. Has to be equal to the downward stuff. Or if you want, you could be formal about the summation here and say that I have to say minus 117.6 equals 0. All right. My preference, though, if I know the acceleration is 0, I just say all the upward stuff equals all the downward stuff put together. Any way you prefer to do it is fine. And so I'm going to get my normal force, so 117.6. And that's a minus 75 sine 50. Oops. This is the moment I discover my calculator is in radians, because that answer made no sense. All right, 117.6 minus 75 sine 50. And I get a normal force now of 60.15. I'll just keep the extra decimal. 60.15 newtons. All right, so again, you look at the problem and think about it in a physically intuitive way, and you go, I'm pulling up a little bit now, so the floor isn't pushing up as hard on it anymore, so the normal force should be smaller than it was previously, and it is. Then I get into the horizontal analysis. F net x equals ma x, and I have this force Fx pulling to the right, and then I have friction pulling to the left, and that A is the thing I'm after. And I'll just plug in what I know about all this stuff, and the x component of my 75 Newton force is going to be 75 cosine 50. And my friction force, I'll write it over here, it's going to be mu k times the normal force. So that's 0.35 times the normal force I just found. And that's equal to 12 times the acceleration. So you just smash all this in your calculator on the left-hand side. I should actually show the calculator once in a while. It's a little bit slower, but it's nice to see it. I think I set this one to degrees already. 75 cosine 50. I like to press enter a lot. There's no harm in doing that. Then minus 0.35 times 60.15. That's the left-hand side of that equation, and then I divide by 12 to isolate A, and I get 4.28 for that. All right, so when you tilt that force upward, there's two competing things going on. If you're trying to cause a large acceleration, I'm not pulling as hard to the right as I was before. But by pulling up a little, I'm decreasing the normal force, which decreases the friction force. So in this case, I actually ended up with an acceleration that was larger than if I just pulled horizontally. Here's a little correction to this. That number came out wrong. Let's go back to the calculator and see what happened. Just check to make sure I'm in degrees. No, it got set in radians. There you go. And I will try again. So 75 cosine 50 plus enter minus 0.35 times 60.15 divide by 12. And I get 2.26 out of it. All right, so actually a little bit less acceleration. So again, just to wrap it up, there's this competing process that happens as you rotate this force vector up. You're making the component that's parallel smaller, but at the same time you're reducing the normal force, which reduces the friction. So it's not entirely clear just by looking at it if you're going to end up with a bigger acceleration or a smaller one. In this case, it turned out to be smaller, but that's a pretty steep angle that I'm pulling up at.